All right, so now we're going to discuss the language of predicate logic at a formal level, the vocabulary, the formation rules, applying the rules to construct woofs, and a few final clarifications. So we're going to formalize our understanding of the language of predicate logic. So far, as you know, we've already developed a feel for how to create woofs in the predicate logic, but we haven't yet explicitly stated the language or the rules that we're developing a feeling for. So now we'll state the language and the rules, and this will allow us to actually show when and why something is a woof in a really explicit way. So I've told you this before, but remember, predicate logic is not this brand new language. It's actually just an extension of propositional logic, an addition of power to propositional logic. What that means is not only that all the inference rules from the propositional logic will continue to apply to predicate logic when we get to the predicate calculus, but that we can even still use our letters, capital P, Q, R, and S, to stand for entire propositions if we ever want to do that. So for example, if P is understood to stand for an entire proposition, things like this are going to be actually well-formed sentences in predicate logic. If you looked at this, you might say, well, clearly this is not, because P is not followed by, say, a name. But in this case, P is just standing for a whole sentence, as it did in propositional logic, similarly with the second expression. So now normally we would only do this, only translate an English sentence using mixed predicate and propositional symbols when one of the sentences doesn't have a predicate logic translation. It turns out that's actually really common. We're just avoiding those sentences for the most part, but just to show you very clearly why this is the case, think of something like, fuchsia is a lovely color. Now that's a perfectly good sentence in English, but you actually cannot translate that into predicate logic. You could try. For example, you might come up with something like this: for all x, if fx and cx, then lx. So for all x, if x is fuchsia and colored, then it's lovely. But this says something like everything that is colored in fuchsia is lovely. It does not say that fuchsia itself is a lovely color. And the reason why we can't do that is that fuchsia is a predicate. And to say that a predicate rather than a thing has some property, we need a much more powerful language. We just can't do it in the predicate logic. We don't predicate properties of predicates. We only predicate them of names, of objects. So whenever we run up against the limits of the expressive powers of predicate logic, what we do is we just drop back and punt and use propositional logic. So a statement like fuchsia is a lovely color, if we had to deal with that, we would just translate it as P or F if you want. On the other hand, we could get a sentence like this where we can actually deal with part of it. Beatrice loves anything fuchsia, and fuchsia is indeed a lovely color. Well, we can deal with Beatrice loves anything fuchsia, right? For all x, if x is fuchsia, then Beatrice loves x. But this part we can't deal with, as we just said. So we're just going to assign that a P, right? So for all x, if fx, then lbx, and P. So this is the complete statement of the vocabulary of predicate logic, which you've already learned, you've already assimilated. So we've got sentence letters, which come from the propositional logic, P, Q, R, and S. You'll notice these are these are at the back of the alphabet. Then we have our predicates from predicate logic, A, B, C. You'll notice that we have the subscript convention to guarantee an infinite supply. So formally, when we're doing predicate logic, we want to really state the language clearly. We say, well, when we're doing predicates, we use everything, all these capital letters in the front of the alphabet, say right up to P, including O, and then we reserve the back of the alphabet for the propositional logic. Now, as I note down here, sometimes for convenience we just don't do that because it's just easier when we're translating from English to use whatever sentence letters seem to fit the occasion. And really, the reality is that we very rarely use propositional logic and predicate logic. And we have our names, which we've learned, and again, we have the subscript convention. We have individual variables. Notice that the names are coming from the front of the alphabet. The individual variables are in the back. And we respect this. We only use the variables U, V, W, X, Y, Z, and T, and really typically we only use X, Y, and Z, though sometimes we'll need a few more. Sentential connectives, which we already know about, quantifiers we already know about, and then the parentheses, which we already know about. Okay, so that's the whole statement of the vocabulary, and then we have the formation rules. Now, the formation rules are all identical to propositional logic, except for one. So we have 1 through 3, which are from propositional logic. So any atomic formula is a WOOF. Now I have asterisked this to remind you that atomic formulas now can be something like, say, P, but they can also be something like, say, Fa or RBA, right? These are all atomic formulas now. Because they can't be broken apart, they can't be made any smaller. They're not connected with any kind of a connective. So, and then if something's a formula, then not that something is a formula. If A and B, if two somethings are formulas, then concatenated with parentheses are formulas. Again, all from propositional logic. And then we have a new one, number 4, which is stated in a way that's actually a little bit different from the way that's stated in the book for clarity. I think this is a little simpler. I'll get to the meaning of this in a second. And then we just have this this final statement, which also occurred in propositional logic, that tells us that the preceding, in this case 1 through 4, are the only ways to make WOOFs in the language. So every formula can be constructed by a finite number of applications of these rules. All right, so the question we want to ask is, what does this rule 4 really mean? So let's see if we can make this clear. So it says, first of all, if AC is a formula with name C, what does that mean? Well, remember, we're speaking the meta language, right? And this AC now basically is telling us, look, if something in the predicate logic is a formula that contains a name, C, right? So anything in the predicate logic that contains some name, C. Now, notice C is not C, just like that particular name, but any name, right? So this capital A can be any predicate, the C can be any name, and it can be any formula whatsoever in predicate logic. So it could be something simple like FA, or it could be GBC, right? Or it could be there exists an XFXA, right? It just has to contain a name somewhere along the line. It could be for all X, there exists a Y such that F, X, Y, and G, D, right? That's a formula too, as you know. Anything that contains a name and a predicate somewhere, okay? So if something is a formula in the predicate logic with some name in it, and then there's some variable V. Now, of course, it's not V specifically, since this is a meta language, so this could be X, Y, Z, those are the ones we use, but we also use U, V, W, etc. So that does not occur. Now, this is very important. So if v is some variable that does not already occur in this formula, then what? Well, then there exists a VAV, and for all VAV are formulas as well. So what does that mean? It means basically if you take an AC, if you take some formula that has a name in it, then you can stick a variable in for that name as long as that variable doesn't occur in the formula already, and then either slap on the existential quantifier with that variable or the universal quantifier with that variable, right? So if you have FA, right, you can slap on, say, actually I don't mean this to be the conditional, it's just an arrow now. There exists an X, fx, right? Or you could write for all y, fy, right? What you're doing is you're inserting a variable in for A and then slapping on the universal quantifier or the existential quantifier, right? Right? Or you could take, say, this formula here. For all x, there exists a y, fx, y, and gd, right? And if you wanted to, you could stick in a variable for the d and then slap on another quantifier out here. So it could be for all z, right? For all x, there exists a y such that f, x, y, and g, z, right? So the operation is very simple. You got yourself a formula, a bona fide formula in predicate logic that has a name in it. Stick in a variable for the name as long as that variable doesn't already occur in the formula. Attach a quantifier to the outside with that very same variable in front of it, and you got yourself a formula. That's all 4 says. Okay, so just to summarize, Rule 4 tells you that something with a quantifier in it is a WOOF only if you can, 1, begin with a WOOF, right, that contains a name, and 2, then substitute a variable for that name, and it's specifically a variable that does not occur, right, does not occur in it, then substitute a variable for that name, and 3, then put one of the quantifiers followed by that variable, either the existential or the universal, at the beginning of the formula. Okay, that's a lot of talk, but it actually just comes down to a very simple kind of substitution. Okay, so what's important to understand here about the formation rules is what they tell us about the relation between variables and names. So, for example, this formula here, for all x, f of x, or there exists a z, gzx, is a WOOF, and you can probably intuitively recognize it as one. But we don't have to use just our intuitions now. We can actually use the rules to prove that this is a WOOF. So how will we do that? Well, just follow along with this form of proof that you're actually already familiar with. So on the first line, this says that FA is a WOOF. Why is FA a WOOF? Well, FA is a WOOF because it's atomic formula. So that's rule 1. Why is GBA a WOOF? Well, GBA is a WOOF because it is an atomic formula. So again, that's rule 1. Now, on the basis of these, of line 2, we can say that there exists a z, gza is a WOOF. Now, why is that? Well, because rule 4, which we just went through, says that if you take gba on line 2 and go ahead and just stick a variable, say z, in for b, and slap on the existential quantifier, right? So we just created exists a z, gza from gba, that's a WOOF too. So now we know that exists a z, gza is a WOOF. Now line 3 says that we can put any two formulas together that we would like to. So let's go ahead and put lines 1 And so let's go ahead and put FA and there exists a Z, G, ZA together in accord with the rules from propositional logic. So put it together with an or, slap some parentheses around it, which you have to do by rule 3, right? So notice now we've got FA or there exists a Z, G, ZA. All mechanical now, just following the rules, right? And then finally, let's go ahead and apply rule 4 again to line 4. So let's go ahead and pop in an X for this A, right? So we'll pop in an X and notice this A is here as well. Now the rule doesn't say that we have to put it in for every occurrence of the constant. We don't, but we can if we want to. It permits us to. So go ahead and put X in for the occurrences of A. And so now we have for all X, Fx, or there exists a Z, GZX. Each time, the cool thing is that each time we've followed a rule. And so we've demonstrated by building things up from the atomic level that this is in fact a woof. So you can see that it's a woof, but now you can prove that it's a woof. Well, let's talk about things that aren't woofs, though, right? So now you can see, I'm sure, that this is not a woof. Why? Because you're saying, well, because look at that Y there. There's no quantifier. That's exactly right. But how do you now prove that it's not a woof? Well, actually, you can't prove that it's not a woof. But what you can do is you can sort of show that, there isn't any obvious way to make this happen with the rules. So you can try, right? Say, take rule 1, right? Go ahead and start with an atomic proposition, say FAB. Now we can create, say, for all X, FXB. We can do that by just substituting X for A, right? And slapping on a universal quantifier. But we can't get for all X, FXY. And why is that? Because there is no rule that would allow us to just stick Y, right, in for B without some quantifier. So there's just no way to do that. So we can also not have multiple quantifiers binding the same variable. So I'm not sure actually if your intuitions are so good at this point that you could see that this is not a woof. There exists an X for all X, FXX. Now that is not a woof. And at an intuitive level, what you would say is you'd say, well, gee, I mean, which X goes with which quantifier? I mean, you can't really tell them apart. So that's at an intuitive level, it doesn't seem like it should be a woof. I mean, one reader might assume that the first X belongs to, the existential X belongs to the first X, or another reader might think that the existential X belongs to the second X. So there's clearly an ambiguity there that shouldn't be tolerated. Well, why do the formation rules show us that it's not a woof? Well, again, just try to make it, right? Start with, say, FAA, okay? So you can certainly make for all X, FAX. That's fine. But now you can't make the next step, because if you were to go ahead and attach an existential on the outside, then you would be and putting another X in for A, then you'd be violating rule 4, because it says that you have to use a variable that's not already in the rule, in the formula. So there's already an X here. So that means you could do this. There exists a Y such that for all X, F, Y, X. That would be perfectly fine because Y is a new variable. But you can't make a formula by adding the same variable again. Note that this does not mean that you can't have like 2 variables in a row or anything like that. It's not what it means at all. So for example, something like for all x, f, x, x. That's perfectly fine. Why is that? Well, because you can take f, a, and then by rule 4, you can just go, there exists an x, f, x, x, right? Just putting x's in for both a's. Okay. So we already know that quantifiers bind variables, not names. But now you can say why that is the case too by reference to the formation rules. So for example, this is not a woof. You know that because you know that for all x, if there's the quantifier here, there has to be a variable on the other side of it, and there isn't one. So how do you show that with respect to the rules? Well, the rules tell you that if you start with an atomic proposition like Fa, right, that if you're going to attach a quantifier to it, you have to stick a variable in somewhere, and there is no variable that's stuck in anywhere. We already know, of course, that this also, I'm sure you're never going to be tempted to do this, is just going to look bizarre to you now. What's happened here? Well, somebody's tried to basically put a variable in for a predicate. No, there just is no way to do that. We have no way in predicate logic to substitute variables for predicates. So again, there's just no rule that allows you to do this. That's always the reason. So we can also now explain why something like this is a woof. For all x, there exists a y, bx, y. Notice that there are no parentheses here. But these are not, right? So these would have all been temptations for you. So surely there's no intuitions initially that tell you that there's something wrong with that. In fact, your intuitions probably were that surely we need parentheses there or somewhere in an expression like this, but you don't. So why is that? Well, look, the answer is there's no rule that permits you to do it. All you only add parentheses using rule 3 from propositional logic, which tells you that whenever you have two formulas, if you want to put them together with an operator, right? So if you have a formula, so remember from propositional logic, like if you have a formula like P or Q and another formula like R, if you happen to want to put them together, you've got to add parentheses. So in predicate logic, that would say that if you have, say, a formula like Fa and another one like there exists an x, Fx, if you want to put them together, you're going to have to add parentheses. That's how parentheses get added. But this is not, you'll notice that none of these have any operators in them, right? There are no operators, there are only quantifiers, and so none of these should have any parentheses in them. If you have formulas that only have quantifiers but they don't have any operators, then you should not be seeing any parentheses. So that's certainly good, and that is certainly good, but that's because of the existence of these operators in both cases. Okay, there's some other important things to understand about the meaning of predicate logic statements. First, formulas containing multiple variables and quantifiers can result from formulas containing multiple names like this. So this is nothing surprising. Start with something like LAB, toss in a quantifier for B, in this case Y, toss in another one for A, and you've got for all X there exists a Y, LXY. That's not surprising at all. But they can also be constructed from formulas containing the same name. So for example, this series of substitutions is perfectly okay as well. Say take LAA, right? You can just substitute, if you would like, a a variable and a quantifier for just one of the a's initially. So there exists a y, L, A, Y. And then you could substitute the final formula. So notice that these two formulas are exactly the same, even though they originated from atomic formulas, one of which said AB, the other of which said AA. And so that's really, in terms of the formation rules, that's why when you see a formula containing multiple variables like this, you can't assume that the formulas have originated from formulas containing different names. So in other words, you can't assume that X and Y are different. They don't have to be. Why is that? Well, look, this formula originated from a formula that contains A only, right? So X would have come from A and Y would have come from A too. So that's just the formation rule way of pointing out that, hey, X and Y are variables. They can apply to anything, including the same thing. So a somewhat related point is the fact that the same variables are used with two different quantifiers doesn't mean that the same object is being designated in each case. Now, I've said this before in an informal context, so let's just make it clear in this formal context. If I have a statement like this, there exists an XLX and there exists an XF of X, that might be a translation of something like this. Something is lucky and something is funny. Now, in English, when we hear something like that, it really sounds like we're talking about two distinct things. But that's just not necessarily the case, right? It could be two distinct things, but it could also be the very same thing, right? So if Alfred is lucky and Alfred is funny, then in fact there exists something that's lucky and there exists something that's funny. And you know what? They're both Alfred. So again, we could show this, straight up using the formation rules, right? So we have LA, right? Change that to exist in XLX. FA, change that to exist in XFX. Put them together. They both came from A. Let's also just remind ourselves of a few facts about the meaning of quantifiers that relates to the order in which they occur. So we said this a long time ago, so let's just say it again. When you have formulas where they only have the universal quantifier or they only have the existential quantifier, no matter how many there are, it doesn't matter what order these occur in, as long as they're woofs. It doesn't matter what order these occur in. So you could have for all X, for all Y, LXY, or you could have for all Y, for all X, LXY. Similarly with the existentials. However, when they are not the same quantifier, it almost always does make a very big difference. So there's a very big difference between for all X, there exists a Y, LXY, which says, say if L means loves, that everything loves something, right? For all X, there is some Y, such that X loves Y. And there exists a Y such that for all X, LXY, which means there is some one thing that everything loves, right? There exists a Y such that for all X, X loves that Y. There is some one thing that everything loves. So those are two very different statements where the order of the quantifiers matters. So mixed quantifiers changes the meaning if you change the order. Same quantifiers does not change the meaning if you change the order. And then finally, when we have an expression with quantifiers that are distributed throughout a formula, they're always equivalent to one in which the quantifiers are all on the outside of the first parentheses. Now, this is something I've emphasized in class, but let's make sure that we really dial this in. So these are equivalent expressions. You'll notice that in this case, there's the existential is on the outside. They're both, the existentials on the outside of the parentheses in both cases here. But in this case, the universal is on the inside, which is, notice it's fine, because the universal is binding the y still. It's not needed out here for this x. So this is a perfectly well-formed formula. This also is a perfectly well-formed formula, but importantly, they mean exactly the same thing. Now, why is that? Well, because the order of the quantifiers is the same. Okay, that's the important thing. And this formula is just this formula that's been achieved by taking the universal out and keeping the order, which means you're inserting it right here. So if you can take these, when you have formulas where the quantifiers are distributed within the formula, you can take them all out, keep them in the same order, put them all outside the first parentheses, and you will have a proposition that means exactly the same thing. However, it also might be a proposition that's not really all that easy to understand in English. So this formula up here might be interpreted as something like this. Say, let F be fried and G be good. So this could mean something is fried and anything that is fried is good. Now look how obvious it is when we're looking at the first formula. There exists an X such that X is fried, and for all Y, if Y is fried, then Y is good. Yeah, that's very obviously a correct translation of this English sentence. Is it the correct English? Is this also the correct one? Well, yes, it is, because we've said they mean the same thing. But when you read it, it's not necessarily so clear. There exists an X that's for all Y, Fx, and if Fy, then Gy. So that's why in class, and why I actually encourage you to, when you're translating English sentences, to allow yourself to distribute the quantifiers closer to the predicates that they're actually applying to, and to the names they're actually applying to. So when we do collect them all on the outside, though, that actually has a name, and we call that putting the formulas into normal form. Okay, that's it.